So in the previous video, we took a look at some of the more intricate concepts of what happens in Kafka behind the scenes. So we just spoke about partitioning, availability, and such. So let's now focus our energies on, um, what happens in terms of consistency on the data, because this is actually the most critical topic to understand from a perspective of designing streaming applications. So, first and foremost, consistency is actually now a consideration that gets split across two different actors in the system, right? The first actor is actually the producer, the second actor is the consumer. And ultimately, consistency is guaranteed in two stages, right? The Kafka giving the guarantee to the producer that the data is actually consistent and available, and then the consumer actually picking up the data that they need in a manner that's consistent. So the consumer actor will actually use their own software or tooling, and that tooling actually plays a critical role in deciding whether the data that's being fed to it is consistent or not. And when we speak about Spark streaming, we'll see how tools like Spark streaming actually play a role of ensuring consistency. But let's focus on the producer side for now, because that's what's under Kafka's control. So for the producer, there are actually three mechanisms or three um, options, right, or configurations. Like we spoke about, first and foremost, the default configuration also is, I believe it's the default configuration, sorry. So it's that all the replicas are in sync. So the primary gets written to, and then the primary partition coordinates with the replica partition. The replica partitions write the data as well into their file system cache respectively, and then they acknowledge, and then the acknowledgements are collected by the primary partition, which then responds back to the producer saying that, look, I'm done. That's one configuration. The second configuration that's possible is only for the primary, which is a leader. I mean, it's also called as a leader partition, only for the leader to acknowledge, and then the uh, replicas are also synced up, but I'm not waiting for those sync ups to complete in order to acknowledge to the producer. So in that kind of a scenario, the sync ups could take, like, let's say, a few seconds more or not. It doesn't really matter. But what matters is that the producer gets a message that the data is actually persisted only based on the leader actually persisting it. So in that scenario, after the leader is actually acknowledged to the producer and before the replicas are synced up, if the leader fails, if the broker hosting the leader fails, then you potentially have a data loss, right? Because the replicas are not synced up yet, and the producer fails, rather the primary fails, and that data is therefore no longer available. But the producer thinks that the data is actually persisted. So that's the pitfall of this configuration option. But obviously, this configuration option has a lower latency, right, as a faster response time than the first configuration option. The third option that's available from a producer standpoint is not to wait for acknowledgements. Obviously, this means that the uh, leader itself might not have finished writing, and already the producer might move on to the next data write. Um, so this is also going to be resulting in data loss if, obviously, before even the leader has written the data to persistent store, the file system cache, and then the disk. Um, if the leader fails, then yeah, that becomes challenging. Uh, so why do you have these options at all? There are use cases for all of this, right? So as you can imagine, the first configuration is the most strict, and that's very appealing for data sets which cannot tolerate the data loss. Like, for instance, payment data coming from the Mintra's mobile application. I absolutely do not want to lose that information, lose that data. So I wait for all of the in-sync replicas to acknowledge, and then I move on. Uh, the second scenario, which is where the leader is only the only one acknowledging, this um, is basically catering to scenarios where it's important that I persist the data, but it's less important that um, I have to wait for all the replicas to sync up, because the scenario of a broker failing is not that common. And because it's not that common, I don't want to optimize, rather, I don't want to uh, lose latency for a scenario that's not going to occur frequently, right? So that's a call a designer can make based on the deployment of Kafka. So for instance, if you're deploying on really robust hardware, right, that rarely fails, then the scenario that the broker is going to fail the moment uh, the the leader has acknowledged it and without but before the replicas have caught up, that could be a very very rare event, right? It's still a non-zero event. It's still a non-zero probability of that happening, but it could be so rare that you're okay to you're okay to tolerate that kind of a scenario to, when that happens, if that happens. So that's, for instance, that could be the case. I'm not saying it is. That could be the case for logging events uh, from the Mintra app for like stuff like adding to the shopping cart, right? In the worst case, um, in the very rare scenario that the user has genuinely added to the shopping cart, but has not, that data is not actually persisted in the replicas and the leader fails, what could happen is the user, when they see the data again, when they see the shopping cart, they might not find that item. So they might have to go back and do it again. So it's a very small inconvenience. It's definitely an inconvenience, but because it's such a rare scenario, um, it's potentially something that you're okay with, right, as a business leader. The third scenario, rather the third configuration, is ideal for um, those scenarios where the volume of data, where the velocity of the data is so large, and the uh, incremental value of the data is minuscule, that it's all right if the data is getting lost every now and then. So again, if you go back to that Mintra example, I would argue that the events corresponding to mouse over, to click throughs, right? And those kinds of events are examples of this category, right? So the mouse over is interesting, obviously, because I can use that information to understand truly what the nuanced preferences for a particular user are. But it's all right if I don't have that data as well. It doesn't fundamentally affect my business in a serious way. So in those kinds of setups, as a producer, like the event collector in the Mint architecture, which is responsible for that data, the mouse over data, could just keep pumping data in, right, without having to wait for acknowledgements. And Kafka just keeps collecting the data. And every now and then, if there's a failure, too bad, that data is lost, and then it just moves on, right? So yeah, so there's a use case for all of it. Okay, just to close the loop on the consumer side, obviously the consumer is very critically dependent on the consumption protocol, but even within the set of tooling that's available, and because Kafka is open source, there's just a plethora of tools, right? Plethora of libraries, in different programming languages that allow you to consume data from Kafka. You have to pay attention to these three fundamental concepts. The first is, are you receiving every message at most once? Which means you might not receive a message sometimes, but you're basically guaranteed that you're not going to get the same message twice, right? And that could be useful for certain kinds of data, like payment, right? But again, what does it mean to not receive payment every now and then? That you have to work it out in your context. The second scenario could be that you receive every message at least once, which means there is no data loss, but there is potentially data duplication. So you could receive a message twice at times, but then you'll have to learn to deal with it, right? How do you deal with the duplicates? In the first scenario, obviously data loss is possible, because at most ones means that at times there could actually not be any copy of the data that actually reaches you for a certain data set, right? Uh, at least once means that there are duplicates that come in, but at least you guarantee there's no data loss. So the payment example could actually be suitable for this as well, right? It depends on your application context. The third is basically the scenario where you're receiving every message exactly once. And fundamentally, when we as humans, as developers, like design systems, we always try to design for this, right? We try to design for a deterministic world where everything happens exactly as planned, and everything just goes smooth, right? The challenge with big data is that that assumption is tested far more often than what you might like, right? So in which case, giving a guarantee or expecting a guarantee that you're going to get deterministically exactly once data, no data loss, no duplicates, is a pretty tall guarantee to give, and that requires a cooperation of multiple different actors coming together. So we're going to spend some time talking about this, in the next few slides. Okay. Um, so let's break down a little deeper, right? At most one semantics, when does that come in? So it's important you understand what happens here. So remember we spoke about offsets. So when a producer produces data, um, the producer is basically saying, I'm going to write all the data um, based on my partitioning scheme, and then the replicas acknowledge it and so on based on the configuration. So that part is done, right? That's the first stage. So let's assume we use the best configuration that guarantees no data loss at all, which means we use the configuration which says all replicas have to acknowledge, and then the leader confirms to the producer that I'm done with persisting the data. Let's assume that's the configuration we use for the rest of this week's lectures. Let's assume that, yeah. Okay, so for consumption, right, what happens to the consumer? The consumer could, obviously the consumer keeps track of his own offsets. We spoke about that being like one of the fundamental decisions that Kafka's design makes. So the consumer um, consumes data. Once it's consumed data from a particular topic, from a particular offset, the offset is saved, which means firstly the offset is incremented, saying that, okay, I've consumed the next message, increment the offset, and then I'm going to do some action on top of that message. Like for instance, I'm going to like do a scoring model, or I'm going to invoke a microservice, or I'm going to record that data somewhere. Like in Mintra's case, they were recording it in storage in that de facto data lake. So all of those are possible. All of those are what I would say is are results, right? So results or outcomes. Let's just use the word results for simplicity. So between the act of consuming the data and saving the offset, basically incrementing offset and saving offset, and the act of uh, performing the outcomes and saving the results, there could be a failure in the consumption pipeline. If that happens, then you have potentially not, rather, you've definitely not done the outcome. The outcome has not been saved yet. The results have not been saved, but the offsets have been consumed. So the offset has been increased and the new offset has been saved, right? So in this case, if you restart the consumer, the default behavior, right, of all these consumers is that I'm going to pick up from where I left off, which is basically meaning I'm going to read from the most recent offset that I have stored. So since I've saved the offset from the previous run, I'm going to read from the saved offset, right? So let's say, for instance, the offset was 10, which means I'm reading the 10th message in that partition. I finished reading, and then I saved the offset to 11, and then there is a failure. So when the consumer is started again, it's going to pick up from the offset that it thinks is where it left off, which is offset 11. But the results from processing the message from offset 10 has not still been saved. So which means those results that in totality apply for all of the messages, like messages 1 through 9, and then 10 and 11 and so on, is going to be incomplete because the result for message 10 is not there. This could be a problem or not, that depends on your application, but this is what at most one semantics corresponds to. So it's not the case that the data is not processed. It could be that, it could be not, but in effect, the outcome that you're expecting corresponding to that data being processed is not there for that subset of data which is missing when the failure occurred. So in this case, it's as though you have not processed offset 10 of the data at offset 10. It's as though you've lost that data at offset 10. In reality, obviously the data is not lost, right? Kafka still has it. You can go back and reprocess it and so on. But if you don't write your consumer in a way that's aware of these failure scenarios, then you could run into this problem. Let's talk about at least once semantics. So in this case, we're talking about the same scenario, which is basically uh, the offset has been consumed, the offset has been written, right? Then there's a failure that happens, and then before the results are saved for offset 10, the failure has created basically a potential data loss. So how do you deal with this? In this case, when the consumer is reset or restarted, um, I could actually have, okay, sorry, uh, there's a typo here. Yeah, sorry. Yeah, let me just uh, go back and repeat this. So we just talked about at most one semantics. So in the at least one semantics, what happens is I save the results of my operation first. So let's wind back again. The processing reads offset 10, right? The message at offset 10 is processed. The result is computed. And when the result is computed, the result is saved. And then the offset is saved to 11, right? So what I've done in this scenario is that I've reversed the order in which the consumer is written. So it first saves the outcome, which is the results, and then it saves the offsets. In this case, there could be a failure again that occurs between. By the way, if the failure occurs before the results are saved, no big deal, right? I just start again, and it's as though I've not processed the data again. It depends on what operation is, but for the most part, it's as though you're processing the data again. And if the failure occurs after the offset, again, no big deal. I've done all the work that's necessary. So obviously the failure is not actually affecting anything. So I can just start the consumer again and it picks up from offset 11 without a problem. So the challenges come in only when failures occur uh, between the two salient steps of saving the result and saving the offset. So in this case, the failure occurs after saving results, but before saving offsets. So I've gone ahead and processed offset 10 message and saved the result, and then a failure occurs. So now, if the consumer is started again, right, consumer is restarted, where does it pick up from? It still is going to pick up from offset 10 because the saving of the offset to offset 11 has not happened yet. The failure has occurred before, prior to that happening. But uh, the offset 10 being consumed means that the message will get processed and the result that gets computed, right, is going to be a duplicate because I've already processed it, I've already saved it, and I'm going to process it again because the failure occurred and I've started again. So how do I deal with the reprocessed duplicate data processing, and what happens to that result? Is that result still meaningful? Do I still save it? Does it have any bearing to the result that was computed the last time around? All of that is like, very advanced, rather, there are custom decisions that you have to make based on the logic, right? So we'll talk about one example of a type of logic that makes it easy to reason about this. But in general, you have to take a look at what those results are, what those outcomes are. You have to take a look at what's called as side effects. Side effects are consequences that happen outside your consumer tool, right? Outside, let's say, Spark streaming. So you could be writing a file to a disk. You could be updating a database. You could be invoking a notification to the end user. All of those are examples of side effects. They're called side effects because they are not in control of your consuming tool. They're not in control of Spark streaming. So in case, rather, they have visible side effects to the external world, right? So in that kind of a setup, if you reprocess the data, while your logic could be written in such a way that reprocessing does not impact anything within Spark streaming, but it's going to produce a duplicate notification to the consumer, or it's going to produce a overwriting entry into the database, which might not be making sense anymore because the database state itself might have changed, right? Or it might be resulting in duplicate data being written to storage. All of those are having various different impacts, right? Because of the fact that those side effects are visible. So you have to take a call based on the development logic that you're writing, whether those kinds of side effects are there, and what is the impact of restarting the consumer. Okay, so that's at least one semantics, meaning you've processed the data once already, you failed, so you process the same data again. How do you reason about correctness? How do you reason about all these side effects and such? In the third semantics that we spoke about, that's exactly once. So exactly once means, like I said, I always have the guarantee that I'm going to get the data processed exactly once, not zero times, not duplicates, like even in the presence of failures. So there are two ways to guarantee exactly once with Kafka. Not just Kafka, like Kafka plus the consumption tool. So remember, just briefly mentioned that your application logic, right? The logic of what happens in data processing is crucial to determine how it deals with those, reprocessing of data and the side effects that come from it. So there's one class of such logic, one type of such logic, which is called as idempotent. So idempotent type of operations are defined as those operations which always produce the same deterministic result um, given the same input, right? Irrespective of the number of different times that you invoke it. So let's take a very simple example. Let's say I'm computing a square of a number, and the number that I'm computing a square of is itself a parameter. It's basically the message that's there in the Kafka topic. So the square is actually a deterministic operation, and you could do it any number of times. But if the number that's input to it is the same, you're going to always get the same output. So 3 square is always going to be 3 square. It doesn't matter how many times you run the square operation, right? So that's an example of a idempotent operation. Let me give you an example of what is not an idempotent operation. Let's say you have an operation that keeps track of the running count of the, let's say it's Mintra again, and you're keeping a running count of number of payments that have happened, number of successful orders that have been placed. So because it's a distributed system, the count has to be like a central count stored in some kind of a database. So all the parallel processing Spark streaming logic will need to consume from there to say what is the latest count and then increment, right? So in that kind of a setup, the count is in a central place. Spark streaming consumers are running separately in their own workers. So therefore, this setup has an externally visible side effect, right? Which is the state that's there in the database that's maintained. So in processing the count, what I do is I take my current message, I look at the nature of the message. If the message is actually going to be like a payment message or order message, then I take the order number that's there in the database and I increment by one, right? Or in simple programming parlance, I read the number count and I do count equals count plus one, right? So that's the logic, and very simple logic. And we again, like I said before, right, we are programmed to think deterministically. We are programmed to not reason about failures. But if we code that running count example in this way, it is not idempotent. Why? Because if it does the job correctly and then there is a failure, I've already incremented the count, and potentially that incremented count has already made its way back to the database. I've already created that external side effect. Now, if I rerun that job, right, I'm not going to get the same count again. So that's an example of what is not an idempotent operation. So the way to make that running count an idempotent operation is basically by doing things like having exactly one semantics be natively ingrained by using various techniques which are available from the database in terms of transactions by Kafka, by the Spark streaming consumer, etc. So all these actors have to come together in order for you to give exactly one semantics for that kind of a problem statement of a running count. Okay, cool. So let's talk about idempotent ops and using that, how can you guarantee exactly one semantics? So here I'm taking the same scenario as the at least one semantic scenario, which is basically the consumer does its job of reading an offset and doing the processing and then saving the result. But here instead of saving the result natively, the operation type is such that I save the result against a naturally occurring unique key. And the naturally occurring unique key could be like a message ID, right? Could be the offset number, as an example. Um, because the offset number is guaranteed to be monotonically increasing, right? And then there is a failure. So before I've saved the offset, there's a failure, and therefore, when I restart this job, right, even though I'm reading from the offset that was previously read already, so let's say offset 10 again, continuing with that example, uh, I come back and compute the answer and I recompute the same result. But when I try to write the result, I notice that the offset, if I use the offset as a natural unique key, I notice that the offset is actually already stored. Um, and therefore, I don't need to compute the result again. So I move on. I go and change the offset to 11, and then life goes on. That way, the results are not recomputed for offset 10. Now, that's another assumption that the natural unique key is actually the offset itself in this case. But in other scenarios, in other contexts, the unique key could be like something that's innately present in the data itself, right? Like the primary key of the data, for instance. That could be like a scenario. Like for instance, most microservice-based architectures provide when they provide events, they provide an event ID. So you could use the event ID as the natural key. So in this case, even though the messages are repeated, the outcome is actually gated on a key, and that key allows you to reason about whether you've already seen that key or not, based on the key that's there in the message compared to the key that's actually stored along with the result. Now this uh, is not going to take care of avoiding side effects from happening. Like for instance, if you publish a notification as part of your results, you can't take it back, right? So therefore, if you run it again, if you run the job again, you'll again send the same notification. So that cannot be avoided. But at least you're able to give accurate results by depending upon this natural key. Okay, so what are the advantages of this kind of a setup? Obviously, this gives you the best guarantee, right? Because it gives you exactly one semantics, and that's, like I said, it's very humanly, it's very intuitive for us to reason about it. So it gives us the feeling of control that we can reason about what the system is doing at any point in time. But with idempotent operations as the backbone, if you exercise this option and then create exactly one semantics, um, it uh, the first advantage is that nothing really changes dramatically in terms of the simplicity of the operation. It's the same operation that you did. It's just that you're now storing like a natural unique key along with the result. So that allows you to reason about whether you've looked at the data again earlier or not. So the idempotent nature of the operation is the critical assumption. So obviously it works well when you have transformations, data processing steps that are shape preserving. So if the shape changes, like shape preserving operations are basically like things like scalar functions or map functions. So that squared example that I talked about, right? The squared is actually going to be the same output when run in parallel, when run with the same input again and again, etc. Doesn't matter. But the disadvantage is that whenever there are aggregates involved, and especially if you are running aggregates, like where you're folding up like a number into a number that you're already computing, then it's not going to be possible for you to use this idempotent operations that like the running count example. Um, in some business contexts, you might not be able to identify a natural unique key, or if you resort to using the offset, the scale of the problem is so large that you're effectively creating a copy of all the data that in Kafka, right? Again, in the results table, the results table could be in a database, in which case the database is going to be as big as the Kafka message queue. That kind of defeats the purpose of, you know, consuming and rolling up and processing the data. May or may not be applicable, so that you'll have to take a look. And it obviously doesn't work for destructive updates. Destructive updates are cases where the action that you perform is actually making a change uh, to the state, the common state, right? So in the running count example, when you do count equals count plus one, you're going back to the count variable or the count field in the database, and you're changing that, right? So that's a destructive update. You can't reverse that. So in those kinds of cases, the idempotent nature does not work, obviously. So obviously, exactly one semantics is not possible. So in this setup, typically what happens is the results are stored in a different uh, a different system, like a database, like I spoke about, and offsets obviously are maintained by the client, and based on the protocol, it could be maintained within. It's usually maintained within Kafka itself. So with that, I'll pause here. I'll I'll give you a glimpse of another way of actually doing exactly one semantics in the next video.